So previously we looked at verifying if solutions to a differential equation were actually solutions. Today we're going to learn how to find the solutions. Remember, the solutions for a differential equation are actual like functions. They're more equations. So a separable differential equation is simply a differential equation where you can separate all the y's and all the x's. So I'm going to write that down. So for like a mini example, with this is a separable differential equation because I can multiply both sides by y. So that way that cancels and then I get y dy dx. But I still have an x on the left side, so I would also multiply both sides by dx. You can do that at the same time. I'm going to, from now on, do it at the same time. So that will cancel. And then we have y equals, no, not y equals, y dy equals x dx. So now all the y's are on one side, all the x's are on another. Sometimes you can't do that, so let me write down a non-example. For dy dx equals sine of x times y, we can't really separate the x and the y. I mean, we could use maybe a product of sum formula, but it still wouldn't work out. Like, we'd have to do something really, really fancy, and then it still wouldn't work out. So this one, you can't just like divide by an x to both sides or something, or divide by a y. You can't easily separate this, so it's not a separable. In fact, you can't separate the x and the y at all. But that would be a non-separable differential equation. It's still a differential equation because it involves the derivative, but it's not separable. So we're going to, in this lesson, we're going to look at how to find solutions to this specific type of differential equation. So we're looking at finding the solutions to separable differential equations. Let's look at the first example. So the first example will say, find a solution to dy dx equals negative 4x y squared. So we're going to find a solution to this. So our goal is to find out like a function that's y equals. So y equals something. That's our goal. And the first step is to actually separate the variables. So I'm going to try and get my dy's to one side, my dx's to the other. And in this case, we're going to have the dy on top. I never want the dx on bottom. Like I never want something where it's like 1 over dx. That doesn't work in the integral like that. This doesn't even make sense. Like if I had 3x squared with the dx on bottom, that will never work. So I never want this dx on the bottom. So really, I'm always going to multiply the dx to the right side, dx, so that goes away. And I want to get my y, or my y's in this case, over to the left side. This is all multiplication here, so I can just divide by y squared. So I get dy over y squared, which is the same thing as 1 over y squared dy. And that's equal to negative 4x dx. Now I have all my y's on the left side, my dy in the top, all my x's on the right side, dx in top. So now we have this. Remember, keeping our goal in mind, I want to get y all by itself. And then this is just a function of x, maybe a function of x and y. But I don't want any dy's or dx's anymore. So how do I get rid of those? Well, the only time I ever see a dy or dx involves an integral. So I'm going to integrate both sides. So after you separate the variables, you can integrate both sides. So first step, separate the variables and the dy and the dx, then integrate both sides. And now I can do this integral. I have all y's, so I'm going to do that. That integral is simply the integral of y to the negative 2 dy. So we'll just take the antiderivative. And this one we don't have to change that much. I'm going to write the negative 4 out front just because I'm used to doing that. So I'll take the antiderivatives now. The antiderivative means I add 1 to that, so that will be to the negative 1. And then divide by that. And then normally we have a plus c. Now in this case, I don't know what c is, but I'm going to call c1 call it C1 because here I'm also going to do that. So I'll have a different C value. Like we're not going to do this every single time, but just for this part, we'll write the C1 and then we'll do this antiderivative. That's x squared divided by 2 with the negative 4 there plus C2. Now remember, my goal is to find y equals, to find a function. So here, well, I'll simplify first. So I have, looks like negative 1 over y, that's this, plus C1 equals negative 2x squared plus C2. Now I want to get the y by itself, so I'll subtract C1 over. Here's the thing. The C values, it's kind of like a shapeshifter. We don't know what C1 or C2 is. So if we take C2 minus C1, if we take two constants and we subtract them from each other, we get another constant. We just don't know what it is. So in fact, instead of writing C1 and C2, I'm going to just change this to C, because it's still some constant that I don't know. So I have over here negative 1 over y equals negative 2x squared plus c. We're just going to say plus c. I don't know what c is. I don't know what C2 or C1 is, so it makes no sense for me to name it anything specific other than just some constant c. And then I'm going to solve for y, and I can just switch those two, right? I could multiply both sides by y and then divide both sides by this, but switching them is just a shortcut. So I have negative 1 over 2x squared negative plus c, and that equals y. So this is actually my solution, and it's a general solution because I can have any c value I want. So we'll call this a general solution. If I plugged in any number for c and I took the derivative, I would still have a solution here that satisfies this differential equation. So a general solution is just when we don't figure out what c is. In order to figure out c, we need some more conditions, and I'll get into that maybe in the next video.